Mr. McBrien, and this is SPH3U, Equations of Motion. Today we're going to dig a little deeper into the mathematics of kinematics and look at deriving the 5 equations of motion and look at some practical tips for how to apply these equations to solve problems. We have really kinematics can be distilled down into what amounts to 2 equations. The first is here, average speed. So if we have a starting speed, a final speed, we take an average of that. That's equal to our change in distance over change in time. Very straightforward. One of the fundamentals of what we're doing here. Now remember that this does imply constant acceleration, so we don't have a changing acceleration in this kind of a problem. And we can also extend this out to the directional case, to velocity. So the average velocity is equal to the total displacement, change in displacement over the time interval. We have a second equation. Acceleration is the change in velocity over change in time, over the time interval. And of course that can be rewritten as v2 minus v1 over delta t. No great shock. We can rearrange any of these equations as we've done in math class. Rearrange any of them to isolate for a given variable. So if we take our acceleration case, if we want to, we can isolate for v2, our final velocity. And what are we saying? We're creating an expression where if we know the acceleration, the starting velocity, and the time, we can get v2, no great shock. And how do we do this? Well, first off, we need to get delta t off the bottom, so we multiply both sides by delta t. That gives us a times delta t equals v2 minus v1. And this is still pretty intuitive, right? The acceleration times the time interval equals the change in velocity. So now to isolate for v2, it's a trivial exercise. We add v1 to both sides, and we get our final expression, v2 equals v1 plus a delta t. Easy stuff, right? Okay, but we can do this for virtually any problem, and we can keep in mind that as long as we have a constant acceleration case, both these expressions apply to any given system. And we can say that our first expression covers everything except acceleration, and our second expression covers everything except distance or displacement. When we combine the two, we can span the entire range of these parameters. In other words, we can solve for any parameter in a kinematics problem. Okay, so let's dig in and talk about an example to illustrate it. So I chose a case here where we need the displacement given the starting velocity, the acceleration, and the time. So a car is going 30 meters per second north. It brakes at 2.3 meters per second squared. After 2 seconds, what's its displacement? So we're not asking for the final speed or the final velocity. We're asking for the displacement. So how do we solve this? In fact, we could do this graphically. So this is just like the weekend homework. We could solve for the area underneath the velocity time graph, just like we did on the weekend, and we could get an appropriate expression. Now, don't get confused. In this case, our particular example, we were braking, so the slope would be negative, but all of the mathematics is the same. Or we can take a purely mathematical approach. So since we don't know, for our car's case, we don't know the final speed, we need to eliminate that from the expression. How do we do that? Well, in our first step, we solve for V2. V2 equals V1 plus A delta T. We can sub it into the other basic expression. So we can sub in for the V2 part that we're not going to solve for today. And what do we get? V1 plus A delta T over 2 equals delta D over delta T. And then from there, it's just simply a matter of manipulating the variables. So we group the V1s together. Then we multiply by, or carry the 2 up into the top. So this gives us V1 plus 1/2 A delta T. But remember, we're still going to be going further. So we multiply both sides by delta T to get delta T off of the bottom here, and we get our distance covered is V1 delta T plus 1/2 A delta T squared. So another example, maybe one not quite so simple in some ways. Excuse me. If we take a car 200 meters from an intersection going 30 meters per second, if it accelerates at 5 meters per second squared, what's its speed when it gets to the intersection? So this is kind of an interesting challenge, right? Because we're not going to know the time when it reaches the intersection, and we're not going to and we don't want to solve for that time if we don't have to. Okay, so what we can do is go and manipulate the variables in the same kind of way and get our V2 squared equals V1 squared plus 2A delta D. And then from there, we can just sub in our starting speed of 30 meters per second and sub in our acceleration and our distance and solve for V2. Now, in any of these cases, really, this is simply a matter of identifying the givens and the unknowns and selecting the equation that relates those variables. So this is where you need to become best friends with your